Hello class, this is Ms. Riggins, and today we're going to be introducing a new unit, and it's talking about the type of functions that we really don't have a lot of experience with, and those functions are called rational functions. And a rational function looks something like this. And as you can see, the parent function for a rational function is f of x is equal to 1 over x. So the domain of this function is every number except 0, because if you were to substitute 0 into the denominator, you would get 1 over 0, which the calculator cannot compute. So as a result, the rational function looks something like this. It has a piece of the graph, a piece of the function above and below the x-axis, above or below the x-axis, except at the point 0. And no matter how far we zoom out or zoom in, the graph will never cross, the function will never cross the y-axis because it will never have an x value of 0. And so what we have here is, since it will never cross this vertical line, we call this vertical line an asymptote. A-S-Y-M-P-T-O-T-E, which basically means a line that the graph will never cross. And usually the asymptotes are determined based off of the domain, which values are not in the domain. So in this case, since x is not in the domain, then that means we have an asymptote at x equals 0. Now if I change this function by shifting it over to the right 1 unit, then that's the same thing as me basically saying, and I'll create another function, g of x is equal to 1 divided by, instead of x, I'm moving it to the right 1, x minus 1. Well, actually, let me move it to the right 10, just so we can have some difference. So as you, oops, I put 20. So as you can see, this new graph, which is blue, now crosses the x-axis, crosses the y-axis, because we no longer have an asymptote at x equals 0. But we still do have an asymptote right here. And where is this asymptote at? It's at the vertical line x equals 10. So wherever the denominator is, whatever makes the denominator 0, that x value lets us know where the vertical asymptote is going to be. So we call the vertical line that the graph will not cross the asymptote. But that's really the vertical asymptote, because it's a vertical line that the line will not cross. Rational functions can have more than just one type of asymptote. All the asymptotes don't have to be vertical. You can also have a horizontal asymptote, and you can also have a slanted asymptote, and I'm going to show you what those look like. So now we have another rational function, and the way that you know it's a rational function is if it has if it's a fraction and it has a polynomial in the numerator and a polynomial in the denominator. That's how you know it's a rational function. In this case, we have two polynomials, 2 degree 2 polynomials in the denominator. And as you can see, if you take a look at the graph, it does cross the y-axis, and in fact, it will always have as its domain all real numbers, because in this problem, there is no real number that I can substitute in for x to make the denominator 0. Because any number that I substitute in for x, then x squared will be a number that is not -1, and I'll always have an answer. So in this case, the domain of this rational function is all real numbers. But as you can see, even though it doesn't have a vertical asymptote, it does have what's called a horizontal asymptote. So if we take a look here, it looks like the graph of the function is approaching a horizontal line, but it never crosses that horizontal line. Well, where is that horizontal line at? As you can see here, if we take a closer look, the graph will pass -5, it will pass -6, but it will never go past -7. So in this case, the horizontal asymptote is at y is equal to -7, because that's the line that the graph will never cross. It approaches and it gets really close to it, but it will never cross -7. Now I know some of you may say, well, it also will never cross 0. And I can understand why you would say that, because the maximum of this graph is at 0. But it's not that we have an asymptote at 0, because as you can see, the graph of the function approached the axis and then went away from it. That's not necessarily an asymptote, it's just a maximum. It went from increasing to decreasing. But what makes the asymptote at the horizontal line y equals -7 is the graph approaches the horizontal line, but it keeps trying to get closer and closer to it, but it never really crosses it. Whereas here at 0, it goes up and away from it. But here in both sides of the graph, as the graph gets closer to y equals -7, it will never ever cross it. That's what makes it an asymptote. So in this case, we do have a horizontal asymptote at y equals -7, but we don't have any other horizontal asymptotes, and we don't have any other vertical asymptotes. So in this case, this rational function only has a horizontal asymptote. Going back to the previous rational function, which has a vertical asymptote, and it has a vertical asymptote at x equals 10. And as you can see here, this vertical line, the graph will not cross. It approaches it on both directions, but it never quite ever crosses it, no matter how far away we get. So we talked about vertical asymptotes and we talked about horizontal asymptotes. Now we're going to talk about oblique asymptotes. And oblique is the same thing as slanted. So now here we have another rational function, and it's rational again because it has a polynomial in the numerator and a polynomial in the denominator. And in this case, as you can see here, this is the graph of this polynomial. And does it have any vertical asymptotes? Well, it looks like it has a vertical asymptote right here at -1, x equals -1, but actually it doesn't, because as you can see, it does cross the y. It does have the point -1, 0, and somewhere down here it's gonna, oh, you know what, it does have a vertical asymptote, but it's between, it looks like between -1, -1.5. But anyway, I do want to talk about, in addition to having a vertical asymptote, it also has a oblique asymptote, which is a slanted line instead of a vertical or a horizontal line, which is a vertical is up and down, slanted is left and right. I mean, horizontal is left and right. This actually has a horizontal asymptote at the slanted line 3x plus 3. Oops. Okay, and as you can see, oh, I'm sorry, I wrote it wrong. Now this may be a little bit confusing, because as we can see here, that the graph does cross the line y equals 3x plus 3, but it only crosses it at this part of the graph. It doesn't cross it down here. And as you can see, as we take a look, as x goes to -infinity, the function values will never ever cross the line g of x is equal to 3x plus 3. And that's why we say it has a slanted asymptote or an oblique asymptote at this point. Now, of course, it does cross it over here. It's because, as you can see, it doesn't seem to be having a problem crossing the graph. But if at any piece of the graph or portion of the graph it approaches the oblique line and doesn't cross it, then that's considered an asymptote. So I know the question that you're asking is, how do we know without graphing if a function has an asymptote, or if it has, and what type of asymptote does it have, or could it even have more than one asymptote? And all those answers will be answered when we take a look at our notes. Okay, so from the notes on page 95, let r of x be a rational function, which means it has two polynomials, one in the numerator and one in the denominator. The numerator polynomial is p of x, and the denominator polynomial is q of x. And the degree of the polynomial, numerator polynomial, is n, and the degree of the denominator polynomial is m. And that's going to become very important when we want to determine, without the graph, what kind of asymptotes the function has. So let's take a look and compare n and m. We have two scenarios. One scenario is when n is smaller than m, which means the numerator polynomial has a smaller degree than the denominator polynomial. If that's the case, then you will have a horizontal asymptote at y equals 0. If the numerator polynomial is bigger than the denominator, the degree of the denominator polynomial, then r is not a proper rational function, it's improper, which means you have two options. If n is equal to m, then r will have a horizontal asymptote, and y is equal to a sub n. So if the degrees of both polynomials are the same, then you will have a horizontal asymptote, and that horizontal asymptote will be at the value y is equal to a sub n divided by b sub n, which are the leading coefficients of the numerator polynomial and the denominator polynomial. So, and I'll show you an example of that later on. And then if n is equal to m plus 1, which means they're only differ by 1, but the numerator polynomial is still larger than the denominator polynomial, then you'll have an oblique or slanted asymptote, and that asymptote will be of the form y equals ax plus b, where a and b are the leading coefficients of the numerator polynomial and the denominator polynomial respectively. And last but not least is when n is bigger than m plus 1. And in that case, that means you're going to have neither an oblique or a horizontal asymptote. And the graph of the polynomial rational function will behave much like the quotient polynomial.